Welcome to this explainer. Let's jump right in. Today, we are going to completely demystify the unseen, incredibly complex infrastructure that powers our global mobile communications. We're looking at a massive, industry-wide transformation going on right now. It is a complete shift from rigid, specialized hardware boxes to highly elastic, AI-driven software.
Think about it for a second. What actually happens behind the scenes when your phone connects to a network? It's something we take for granted every single day, right? Just marvel at the seamless magic happening in mere milliseconds every time you buffer a 4K video on the train, or when your phone effortlessly switches between towers while you're driving down the highway. What is the invisible machine making all of that happen?
Well, a big part of the answer lies in the sheer physical scale of the telecom world. On one hand, you have this perfectly seamless, lightweight user experience on a device that literally fits in your pocket. But on the other hand, supporting that is an immense, unseen architectural complexity, spanning cities and continents, relying on massive towers and miles of cables. But what's really fascinating is how the actual brains of these towers have evolved over the decades.
To make sense of it all, we're going to trace this evolution across 5 quick steps, starting with the circuit-switched era, moving through 4G, unpacking Open RAN, looking at automation, and finally, seeing it all from the operator's perspective.
So let's start at the beginning with part 1, the circuit-switched era.
Back in the early, hardware-heavy days of 2G and 3G, networks were incredibly rigid. They were strictly hardware-based and relied heavily on circuit switching just to route simple voice calls. Now, telecom is famous for its alphabet soup of acronyms, but actually, scratch that. Let's simplify these into concepts we all understand. Think of the HLR, the home location register, as the master VIP guest list for the entire network. It holds your main profile. The VLR, or visitor location register, is basically the local hotel registry when you travel. It temporarily holds your data while you roam into a new area. Then you have the MSC, acting as the main switchboard operator routing your call, and the EIR, acting as the bouncer, checking your phone's unique hardware ID to make absolutely sure it hasn't been reported stolen.
The crucial point here is that every single one of those baseline functions required a totally dedicated, specialized hardware box. Take security, for example. The OSSI is a piece of hardware designed specifically to do a mathematical dance. It takes a secret key securely burned into your SIM card. And by the way, this key is never actually transmitted over the air, and it generates what are called secure triplets. These triplets allow the network to authenticate you and encrypt your calls perfectly. It's a really elegant system, but because everything was permanently tied to specialized physical hardware, upgrading it was an absolute nightmare.
But then, the smartphone boom happened. Apps took off, and a massive explosion of mobile data meant the old voice-first model on legacy 2G and 3G systems was completely buckling. Networks had to adapt, abandoning that old setup for a packet-switched, data-first architecture called All-IP.
Which brings us to part 2, 4G and the All-IP shift.
To handle this tsunami of data without total system collapse, the architecture had to become much flatter. The biggest breakthrough here was the complete separation of the control plane from the user plane. The MME, or Mobility Management Entity, stepped up to act purely as the traffic cop. It pages your phone, manages handovers, and handles security. But, and this is key, it doesn't touch your actual Netflix video data. That heavy lifting is offloaded entirely to the user plane, specifically the serving gateway and the packet data network gateway, which serves as the ultimate exit point out into the broader internet.
By making everything Internet Protocol, or IP-based, operators were finally able to handle those high-speed data rates and dramatically lower packet latency. Fun fact though, this new core network didn't even have a native way to handle traditional circuit-switched phone calls at first. It literally had to use a workaround called circuit-switched fallback just to let you make a voice call. But this flattened, IP-based network successfully set the stage for an even more radical transformation that was just around the corner.
And that is part 3. Open RAN and disaggregation. This is where software truly starts eating the telecom world.
To ground this highly technical architecture in real-world business realities, we have to look at what telecom operators are actually dealing with today. They are facing escalating demands for 5G capacity, which means they have to spend massive amounts of capital and operational expenditures. At the same time, they're historically locked into proprietary infrastructure from a very small handful of legacy vendors. No competition means high prices. So operators are desperately looking for ways to lower cost, break these vendor monopolies, and make it economically viable to connect remote, lower revenue markets.
The ultimate solution to this hardware lock-in is Open RAN.
The Open Radio Access Network movement completely disaggregates or separates the physical cell tower hardware from the software. Instead of buying a proprietary all-in-one black box from one company, operators can break the tower down into distinct parts: the radio unit up on the mast, and the distributed unit and centralized unit processing the data below. Because the interfaces between these units are now open and standardized, operators can run highly complex network functions purely as software. And the best part? They can host it on commercial, off-the-shelf servers like standard Intel Xeon processors, rather than insanely expensive custom-built telecom hardware.
Now, the absolute star of the Open RAN show is the RIC, or RAN Intelligent Controller. Think of this as the central brain of the new mobile network. It comes in two distinct versions: a non-real-time version that sits high up in the management layer, training machine learning models, and a near-real-time version that lives right down close to the edge. The RIC hosts microservices called XApps and RApps that actively learn, optimize the radio environment, predict user traffic, and automatically steer resources before a bottleneck even happens. It's a total game changer.
Which brings us to part 4, automating the future.
With software now fully decoupled from hardware, driving a truck out to a remote cell site just to do a manual upgrade is a thing of the past. Instead, a 4-stage pipeline completely alters the economics of the network. Stage 1 sets up the cloud environment. Stage 2 uses zero-touch provisioning. That means a new cell site powers on, connects, and configures itself automatically without a human touching it. Stage 3 implements CI/CD, which allows operators to deploy software upgrades and bug fixes across thousands of cell sites in just minutes. Finally, Stage 4 applies AI and machine learning to continuously optimize performance. Implementing this pipeline can literally save operators up to 40% in operating expenses.
So, let's look at what this all means in part 5, the operator's perspective.
How does this shift actually impact the companies building the networks? For a major global player like Etisalat, which serves over 150 million subscribers, Open RAN isn't just some fun science experiment. It is the fundamental key to scaling their networks affordably. If you look at the goals for smart cities, autonomous vehicles, and the Internet of Things, operators must now support a staggering 1 million connected devices per square kilometer. You simply can't physically or financially achieve that kind of extreme network elasticity using old closed-box hardware.
And that leads to a definitive realization from top-tier operators. This quote really hits the nail on the head. The era of specialized, single-purpose hardware boxes is completely over. Software is now the undisputed primary component of telecommunications. By fully cloudifying their architecture, operators are throwing the doors wide open for artificial intelligence to manage and optimize our communications at a level of complexity a human engineer could frankly never achieve.
And so we arrive at a critical inflection point. As artificial intelligence officially takes the wheel of our unseen mobile infrastructure, dynamically steering traffic, healing outages before we even notice them, and scaling capacity in milliseconds, how will these hyper-automated networks change what we build on top of them tomorrow? I really hope this explainer leaves you wondering just how limitless our global connectivity will become as AI optimizes every single millisecond of our digital lives. Thanks so much for joining me on this incredible journey through the unseen network.